understanding power electronics. In this video, we'll go through and understand how buck converter operates under discontinuous conduction mode. Let's get started. This is the buck DC-DC converter. When we say discontinuous conduction mode, we are talking about the inductor current. It is the inductor current that is not continuous. It is not continuous in the sense that we are going to define. We will now see the inductor current waveform, how it will look under continuous conduction mode and discontinuous conduction mode, and see where the difference lies. As you are aware, the switch is switched on for T on interval, switched off for T off interval, and the period is Ts. We are assuming constant frequency of operation. The period Ts remains constant. The duty cycle is T on by Ts. ILC is the inductor current under continuous conduction mode or CCM. The average forms the load current. This is the average current. The load current is IOC. And the ripple part goes through the capacitor. The slope of the current will be Vin minus V0 by L during the T on interval. During the T off interval, the inductor current freewheels through the diode and the inductor current slope will be minus V0 by L. As we reduce the load, the output voltage remains the same because output voltage is duty cycle times Vin. As we reduce the current, at some point, the inductor current is just going to return to zero at the end of the T off interval, and then immediately the switch is switched on and the inductor current rises again. This is the boundary operation. The orange curve ILB is the boundary current. The average of the ILB curve is the boundary output current IOB. When you reduce the load current even lower than IOB, then the operation switches to discontinuous conduction mode. So the green curve corresponds to the discontinuous conduction mode of operation. We will see the detailed waveforms shortly and how they arise, etc. The essential difference between continuous conduction mode operation and the discontinuous conduction mode of operation can be understood by seeing the blue curve and the green curve. Under CCM or the continuous conduction mode of operation, there are two intervals within one period. The first interval is T on, when the switch is on and the switch is conducting. The diode is off and not conducting. So the second interval is during T off, when the switch is off, is not conducting, but the diode is on and it is conducting. Under DCM operation, as you can see, there are three intervals. Number one, again T on. When the switch is on and the switch is conducting, diode is not conducting. That's the same as before. The second interval is the TF interval, freewheeling interval. When the switch is off, switch is not conducting, diode is conducting. The third interval is the TD interval. When the diode is off, switch is off, neither of the devices are conducting. In this mode of operation, the buck converter goes through three intervals of operation, and that distinguishes it from the CCM operation. There are two videos in this series, Understanding Power Electronics, on continuous conduction mode. There is one video on the boundary operation between continuous and discontinuous conduction mode. You may wish to go through them in order to familiarize yourself with continuous conduction mode operation and boundary operation. With that as a quick introduction to DCM operation, we will go through the ideal operation of the converter under DCM conditions in a more detailed manner. Next, we will see the ideal operation of this converter under DCM. We will make the usual assumptions that the operation is ideal, The switches and diodes and other components are ideal, and we'll assume that the operation has reached steady state and the output voltage V0 is almost pure DC. That means capacitor C is large. So these are the assumptions we make. We will plot three waveforms. One is VA, the voltage at node A with respect to this common point. Second is the inductor voltage. Third is the inductor current. We will understand the operation through the three waveforms. So at the start of the period, we switch on the switch. The current starts to flow through the inductor. VA during the T-on interval is Vin. This side of the inductance is connected to A. This side of the inductance is connected to V0. So the voltage VL will be Vin minus V0. And this voltage is applied across the inductor. Since VL equals L dIL by dt, the slope dIL by dt will be VL by L. So the inductor current rises at a constant slope Vin minus V0 by L and reaches IP. It is going to start from 0 amperes. There will not be a pre-existing current. We will show that shortly. Now at T-on, we switch off the switch. As the inductor current starts to fall, the induced voltage VL will be in the opposite polarity. That will overcome the voltage V0 and forward bias the diode, and the freewheeling action will take place. The inductor current will flow through the diode. This is as before in the continuous conduction mode. Once the diode conducts, the inductor voltage is clamped at minus V0 because V0 is applied across the inductor in the opposite polarity. So the slope of the current here is minus V0 by L. The current is not sustained throughout the off interval. Before the end of the off interval, the current comes and hits 0. When the current tries to go negative, the diode will block it because the diode cannot conduct current in the reverse direction. So the diode stops conducting at this point. Interval TF is the freewheeling interval, which is different from T-off in this case. Once the current hits 0, it stays at 0. The switch is off, the diode has also stopped conducting. So the only thing that stays alive in this circuit is the capacitor and the load. The capacitor feeds the load. So the capacitor sustains the output voltage V0. I will plot the waveforms here and then I'll explain. First, let's look at the IL waveform. IL waveform, the current is 0. Because the current is 0, dIL by dt is 0. So VL is 0. And if you look at the voltage VA, it is V0 plus 0 volts because the inductor voltage is 0. So VA will be equal to V0. So this interval is the discontinuous interval TD. So the T-off, the off interval, is split into two parts. The freewheeling interval and the discontinuous interval when neither of the devices is conducting. Now the period has ended here. The inductor current is 0 at the end of the period. So the next cycle, the inductor current will start from 0. So when you switch on the switch again, once again, the voltage VA becomes equal to Vin. VL becomes equal to Vin minus V0. And the current rises at a slope Vin minus V0 by L to a value IP, peak current. Now again, the switch is switched off and the inductor current freewheels through the diode. VA is 0 and VL becomes equal to minus V0 and the current falls from IP down to 0 in an interval TF at a slope of minus V0 by L again. Once again, during the discontinuous interval, the switch is off, the diode is off, and the capacitor sustains the load current. So this process repeats. So this is the discontinuous conduction mode of operation. The VA voltage has a DC component and a periodic part. The periodic part has switching fundamental and the harmonics. The business of this LC filter is to get rid of the fundamental and the harmonics and just let the DC part in VA to go through. So the DC part or the average part of VA is the output voltage. So that is V0. Notice that V0 goes through this part here because this voltage is also V0. This part of the VA waveform that will correspond to V0. The average of the inductor current flows through the load. The DC current cannot flow through the capacitor. The remaining part of the current or the ripple current of the inductor current flows through the capacitor. Almost all of the ripple current will flow through the capacitor. The capacitor will absorb it while producing very little ripple voltage. Next, we will compare the CCM operation and DCM operation through waveforms. This shows the CCM waveforms. Again, the same three waveforms. VA, the voltage at node A, VL, the inductor voltage, and IL, the inductor current. We are again plotting the CCM waveforms under steady state, assuming ideal operation. When the switch is on, the voltage VA goes to Vin, VL goes to Vin minus V0. This is as in the DCM case. Because the voltage Vin minus V0 is applied to the inductor current goes up at the rate of Vin minus V0 by L. The only difference is, in the case of CCM, it starts from some value I1 and then goes to value I2. In the case of DCM, it always starts from 0 and goes to IP. And then at T on, the switch is switched off. The inductor current freewheels through the diode. As the current freewheels, assuming the diode voltage to be ideal, VA will be 0. So the voltage VA is at 0 in both CCM and DCM cases. There is no difference. As the current freewheels through the diode, the voltage across the inductor will be minus V0. The inductor current comes down at a slope of minus V0 by L. This is also the case in DCM. In the case of DCM, the current comes down to 0 before the end of the cycle. In the case of CCM, the current continues to flow throughout the T-off interval and goes back to I1 at the end of the cycle. In the case of DCM, the inductor does not have sufficient energy to keep the current going throughout the off interval. And the current falls to 0, and once it falls to 0, it stays at 0 during the discontinuous interval. In the case of CCM, there is no discontinuous interval. That is the critical difference between CCM and DCM. The current comes to 0. When the switch is switched on again, the inductor current starts from 0 and rises. In the case of CCM, the current has fallen to I1 and not to 0. So, and the current goes from I1 up again when the next cycle starts. So, in the case of DCM, there are three intervals: T-on, TF, and TD. The T-off interval is split into two sub-intervals: the freewheeling interval and the discontinuous interval. Whereas in the case of continuous conduction mode, there are only two intervals: T-on interval, T-off interval, which is also the freewheeling interval. So the discontinuous interval is absent in the case of CCM operation. Next, we will look at the output voltage. One way of arriving at the output voltage is to consider volt-second balance. Under steady state in an inductor, integral VL dt must be equal to 0. That means the area under the voltage curve over a period must be equal to 0. Or if you look at the CCM waveform, A plus plus A minus must be equal to 0. you can do this and you can arrive at the output voltage V0 equal to dV in. In the case of discontinuous conduction mode operation, the freewheel interval goes down, but you can also expect V0 to change. So it's a bit more complicated to see intuitively what happens by looking at the VL voltage waveform and considering the volt-second balance. So we will look at the VA waveform. So we know that the average of VA voltage is the output voltage. The average of the VA voltage will be the area of the VA voltage over a period divided by the period. Area of the VA voltage will be the area A0, V in times T on. So the output voltage will be V in times T on by Ts, which is V in times duty cycle. So V0 is D times V in. In the case of discontinuous conduction mode, this area here is A0 because that is V in times T on. But the voltage waveform has this extra area delta A0, that is V0 times TD. The area under the voltage waveform VA over a period in the case of DCM is greater than it is in the CCM case. So you can expect in the case of DCM, the output voltage will be more than dV in. We don't know yet what it is. We will derive an equation as we go along. We can see conceptually that V0 has to be more than dV in. This is generally the case in DCM operation. The output voltage will tend to be higher than in the CCM case. Next, we will derive an equation for the output voltage under discontinuous conduction mode. One way we can do it is to use volt-second balance. That's how we did in the case of CCM operation. When we apply volt-second balance to the inductor, 0 to Ts, integral VL dt is 0. This is true of any converter under steady state. In fact, this will be true for any circuit under steady state. The area of the voltage waveform over a cycle must be 0. That's what this integral means. That means A plus A minus equal to 0, as we saw. And we can write this as V in minus V0 times T on plus minus V0 times TF equals 0. From this equation, you can solve for V0 by V in. V0 by V in is T on by T on plus TF. We do not know TF. So we have to find a relationship between TF and V0 in order to proceed further. We will do it by an alternate method, perhaps a bit simpler, but either method is fine. In this method, first we will find the average switch current or the average input current. Notice that the switch current and the input current are the same. The switch is in series with the source. So I in equals Is. So this is the inductor voltage waveform. When the switch is on, the voltage is V in minus V0. When the switch is off, during the freewheeling interval, the voltage is minus V0. And then during the discontinuous interval, the voltage will be 0. The inductor current starts from 0, goes at a slope of V in minus V0 by L to a value IP, some peak. And then when you switch off the switch, the current falls at the rate of minus V0 by L, hits 0 after an interval of TF, and then stays at 0 during the discontinuous interval. If you look at the inductor current, during the T on interval, the inductor current flows through the switch and hence is the input current. During the T off interval, the inductor current freewheels through the diode, hence it is the diode current. So this part of the inductor current is Is, this part of the inductor current is Id. We can plot these two waveforms now separately. Is waveform is as shown. starts from 0, goes to IP, and then abruptly falls, and then stays at 0 till the switch is switched on again. And the diode current suddenly jumps to IP when the switch is switched off, and then falls to 0 at the end of the freewheeling interval. At this point in time, the current jumps from the switch to the diode. That is the commutation phenomenon, the current jumping from one branch, the switch here, to another branch, the diode. The average of the switch current is the input DC current. I can determine the average by integrating the switch current over a period and then dividing it by Ts. That is taking the area AS and then dividing that area by Ts. Fortunately, area AS is a simple figure, it's a triangle. Area is half IP times T on. So the input DC current is half IP times T on divided by Ts. T on by Ts is of course the duty cycle. So this is IP duty cycle by 2. That is the DC input current. We can find the value of IP by taking the slope of the current, which is Vin minus V0 by L, multiplied by the interval T on. So IP is Vin minus V0 by L times T on. T on is DTS. T on, the on interval, is duty cycle times the switching period. Combining the two, the DC input current will be Vn minus V0 by L times DTS times D by 2. So I rewrite this equation in this form, D and D combine to form D square, and Vin I pull it out and it becomes 1 minus V0 by Vn within the bracket, and the rest of the terms I combine together to form Vn Ts by 2L. This is an equation that relates V0, the output voltage, and the input current. We assume we know the duty cycle, we know the switching period, we know the inductance value, we know the input voltage. So this gives the relationship between output voltage V0 and the input current. But we don't know the input current. So what should we do? So step 2 of this method is to find the relationship between input current and output current. Because we assume that we know output current because we are connecting the load to the circuit, so we know how much current we are drawing. So for that, we use input-output power balance. This is an idealized converter. The power loss within this circuit is 0. The inductor and capacitor draw energy every cycle, absorb it, and then return it within the cycle. There is no part in this circuit where power loss is occurring. All the input average power goes through. Input average power equals output average power. Output average power is output DC voltage times output DC current. Input average power is input voltage, which is DC, times the average switch current or the DC input current. As we know, it is only the DC current that will contribute to the average input power. The AC part of the input current does not contribute to any average power. Equating the input average power and the output power, we get V0 I0 equals Vin In. Here, Vin is assumed to be known. We are applying some voltage to the circuit. I0 is assumed to be known because we are connecting some load and drawing some power. Combining this equation with the earlier equation that we got, which related In and V0, combining the two equations, we will get the output voltage. That's what we'll do next. Now we come to the main event. We want to develop the equation for output voltage. We have got this equation which relates I in, the input DC current, with the output voltage. We have got this equation based on power balance. The first equation relates I in and V naught. The second equation also relates I in and V naught. V in and I naught, we assume that we know the input voltage. We are applying the input voltage. And we know the load current because we are drawing so much current from the circuit. So we have two equations, two unknowns. We know how to solve that. So I can write I naught as V in by V naught times I in. Substitute for I in from 1. So I will get I naught equals V in by V naught times V in Ts by 2L times 1 minus V naught by V in d square. I can take V in by V naught inside the bracket. Then I will get I naught equals V in Ts by 2L times V in by V naught minus 1 d square. That's it. We are done. So how did we do it? We first found an equation for the input DC current, and that related the input DC current to the output voltage. Then we used power balance to get another equation relating I in and V naught. Combining these two, we have got this equation. We are expressing this as an equation for I naught. We can rewrite this as an equation for V naught. So this is the same equation. I naught equals V in Ts by 2L times V in by V naught minus 1 d square. I can rewrite this equation with V naught on the left hand side. That means V naught as the subject of the equation. You can take a piece of paper and do that. If it is done, then V naught will be d square by d square plus a term I naught by V in Ts by 2L times V in. Please try and rewrite that equation in this form. Finally, we have an equation for V naught. It is not a too complicated an equation, but it doesn't have the simple elegance of V naught equal to dV in. In the CCM case, given V in, the output voltage will depend only on the duty cycle. Here, given V in, the output voltage depends on the duty cycle and also the load current and also the frequency, the period, and also the inductance. If you assume that the frequency and the inductance are fixed, the output voltage will depend on the duty cycle, the load current, and the input voltage. So with the load current, the output voltage will vary drastically in DCM. This is typical in DCM operation. Next, we will normalize this equation in order to express it in a simple form which is useful across scales of design. So one converter may be working at a particular frequency and delivering a particular output. Another converter may be operating at a different frequency and delivering a different output power. Normalization allows us to compare the two designs. There is a video in this series on buck converter boundary operation where the normalization is discussed in a bit more detail. You may want to take a look at it. Note that once we normalize the equations, the variables are dimensionless. There are no units. That is something to keep in mind. We will be using what I call base V in normalization. Again, this is introduced in buck converter boundary operation video. Here, the normalization factor or the base value Vn equals V in. We can take V naught also as the base value. We will do that later in another video. In this video, we will be using base V in, which is a natural base to take. You know the input voltage, so you are using that as the normalization factor or the base. The In the base for current is V in Ts by 2L. You remember in that equation we had the term V in Ts by 2L. We are going to use that as IN. That is convenient for us. Normalization has to be consistent. The normalization factor for resistance or impedance cannot be arbitrarily chosen. It has to be Vn by In, that is 2L by Ts. Likewise, if you are having power normalization, that should be Vn times In. Notice that the base current In V in Ts by 2L, the unit is amperes. You may check it out. Now we will normalize the DCM equation using base V in. The DCM equation is V naught equals d squared by d squared plus within brackets I naught by V in Ts by 2L times V in. Base V in, let me rewrite here, Vn is V in and In is V in Ts by 2L. Now it becomes obvious why this set of normalizing factors makes sense here. If I bring the V in over to this side, V naught by V in, that is normalized output voltage. I naught by V in Ts by 2L, that is normalized output current. So VON is the normalized output voltage, that is V naught by V in. ION is the normalized output current, which is equal to I naught by In, which is equal to I naught divided by V in Ts by 2L. I can rewrite this equation as VON equals d squared by d squared plus ION. So it's in a fairly compact form now. And this equation is valid for all designs. I don't have to substitute the values of L and Ts, etc. separately. Next, we will do a simple check on this equation. I'm reproducing the output, normalized output voltage, VON equals d squared by d squared plus ION. The base Vn is V in, In is V in Ts by 2L. Remember, you have continuous conduction mode, discontinuous conduction mode, and in between is the boundary operation of the converter. At the boundary, the CCM equations must be valid. At the boundary, the DCM equation must be valid. In the video on the boundary operation of the DC-DC converter, we derived an equation for IOB, the boundary current. This shows the waveform of the boundary current. The current starts from 0, goes to a peak IP at the end of T on switching interval, and then when the switch is off, the current comes down at a slope of minus V naught by L, and then comes to 0 exactly at the end of the cycle. And immediately the switch is turned on again and the current rises again. So this is the boundary condition. You can view this condition as the limit of the continuous conduction mode operation. In continuous conduction mode operation, normally the current does not start from 0. So at the limit, as we lower the load current, at the limit, the current starts from 0. In DCM operation, a discontinuous interval Td is present. This represents the limit where Td becomes 0. So this is the limit of the DCM operation where the Td has become 0. This is the limit of the CCM operation where the starting current has come down to 0. Now, this boundary current is IOB is delta IL by 2. It was done in the earlier video. Boundary current is delta IL by 2. And this is the equation for boundary current. Here I am giving it without further explanation. The boundary current is Vn by 2L d times 1 minus d. Again the same factor Vn by 2L. Now I can normalize the boundary current Boundary current is also a current, so I can use the same normalization factor. So IOBN is the normalized boundary current using the same base Vn, that will be d times 1 minus d. This boundary current must satisfy the DCM equation also. So I can substitute this IOBN in that output equation. If I substitute for IOBN d times 1 minus d, we will get d squared over d squared plus d times 1 minus d. D times 1 minus d will be d minus d square. So d square and d square will cancel and VON will be d. That is the output voltage ratio under continuous conduction mode. This is a check on our derivation. In subsequent videos, we will plot these equations together to see visually the complete DC steady state characteristics of the converter. We will also do some problems so that the usage of these characteristics become clearer to us. With this, we have come to the end of this video. In case you find this video and the series of videos useful and interesting to you, please subscribe to this channel and also click the link. Thank you.